13.8 billion years ago, everything we know exploded into existence from a point smaller than an atom. This has been our story, our cosmic genesis, the bedrock of our understanding. But the James Webb Space Telescope, an instrument of impossible precision, a $10 billion eye designed to gaze upon the universe's infancy, has just found galaxies that were already ancient when the universe was supposedly still a baby. We are seeing stars that formed heavy elements before the cosmos had time to cook them, massive black holes that grew impossibly fast, and structures so perfectly organized they shouldn't exist in a chaotic, young universe. The most powerful telescope ever built wasn't meant to destroy our origin story, but that's exactly what it's doing. Prepare yourselves. We begin. The James Webb Space Telescope cost $10 billion and took 30 years to build. This monumental effort, a testament to human curiosity and engineering, was not just about getting better space photos. Scientists had a specific, profound mission to prove that our story of cosmic creation was absolutely correct. For decades, we have told ourselves a simple, elegant tale. The Big Bang happened 13.8 billion years ago. Then came 400 million years of cosmic darkness, a silent, starless epoch while the universe cooled and gravity slowly, patiently, began to gather the primordial gas. Those first stars, when they finally ignited, were supposed to be simple, monstrously large, and made only of hydrogen and helium, the raw ingredients forged in the initial fireball. Galaxies, in this narrative, should have grown gradually, messily, over billions of years through countless collisions and mergers, like cities built slowly from scattered villages. This timeline was not just a theory. It was the foundation of modern cosmology. Every textbook, every documentary, every elegant equation that described our universe relied on this sequence of events. The standard model of cosmology, a framework of stunning predictive power, was built upon this assumption of a slow, hierarchical formation of structure. The James Webb Telescope was designed to be the ultimate witness to this process. Its unparalleled infrared vision could peer back through the expanding darkness, through the veil of cosmic dust, to the very edge of the cosmic dawn. It was meant to show us those first primitive stars struggling to ignite, to capture the faint, red-shifted light of the first fledgling galaxies as they flickered into existence. We expected to see a chaotic, violent universe slowly, painstakingly, organizing itself into the cosmos we know today. The telescope's 18 hexagonal mirrors, coated in a whisper-thin layer of gold, were polished to a perfection measured in atoms. Its instruments were calibrated to detect the faintest whispers of ancient light, photons that had traveled for more than 13 billion years to reach us. Scientists prepared to celebrate as the first observations confirmed what their powerful computer simulations had predicted for decades. The early universe should look young, disorganized, and exactly as messy as you would expect from a cosmos just learning how to exist. But when James Webb opened its golden eye and looked back toward the beginning of time, it did not find confirmation. It did not find the expected chaos. It did not find the primitive, stumbling galaxies of our theories. Instead, it discovered something that made astronomers question everything they thought they knew about cosmic history. The discoveries staring back at us from the cosmic dawn challenged not just the details of how galaxies formed, but the entire timeline of cosmic evolution. The implications reach far beyond astronomy. If our most fundamental story about reality is wrong, what does that mean for physics, philosophy, and our place in the universe? The telescope that was meant to prove our origin story might instead destroy it completely. 400 million years after the Big Bang, the universe should have been a cosmic wasteland. To put that into perspective, if the entire history of the cosmos was compressed into a single calendar year, we are looking at January 2nd. At that point, Galaxies should be tiny, primitive collections of the very first stars, little more than glowing smudges in the endless dark. What James Webb found instead were massive, mature galaxies that looked as if they had been around for billions of years. These are not small collections of newborn stars struggling to survive. We are seeing galaxies with masses equivalent to 100 billion suns, perfectly organized into spiral arms and central bulges. Our own Milky Way galaxy took over 13 billion years to reach this level of development. Yet here are galaxies that somehow achieved this complexity when the universe was barely out of diapers. The numbers simply do not add up. Our most sophisticated computer simulations, which have successfully modeled the evolution of the universe for decades, show that galaxies this massive should take at least 2 billion years to form. Through the slow, arduous process of smaller galaxies merging together. But we are seeing them when the universe was only 400 million years old. It is like finding a fully grown oak tree in a garden that was planted yesterday. Dr. Ivo Labbé from Swinburne University described these discoveries as galaxy monsters that shouldn't exist. His team found galaxies so massive, they make up almost as much matter as all the stars that should exist in the entire observable universe at that time. The math simply does not work with our current understanding of cosmic evolution. It is a statistical impossibility, a cosmic contradiction written in the light of ancient stars. Even more puzzling is how organized these galaxies appear. The Big Bang Theory predicts that early galaxies should be chaotic and irregular, slowly forming structure through gravitational interactions over cosmic time. Instead, James Webb is showing us galaxies with clear spiral patterns, well-defined central bulges, and organized star formation regions. These are features that should take billions of years of quiet, stable evolution to develop. This discovery is forcing astronomers to confront an uncomfortable possibility. Either our understanding of how fast galaxies can form is completely wrong, or our timeline of cosmic history needs a major revision. Some scientists are beginning to whisper about alternative theories that could explain these observations. Theories that were once dismissed as fringe ideas. But accepting those alternatives means abandoning much of what we thought we knew about the universe. The implications stretch beyond just galaxy formation. If massive, organized galaxies existed this early, they would have profoundly influenced the entire structure of cosmic evolution. The gravitational effects of these monster galaxies should have left traces throughout the universe that we simply do not see in other observations. Yet, the evidence keeps mounting that these impossible galaxies are absolutely real. In the beginning, the universe knew only 3 elements: hydrogen, helium, and tiny, almost negligible traces of lithium. Every other element in the periodic table, the building blocks of planets, of life, of you, had to be forged inside the nuclear furnaces of stars and scattered through space when those stars died. This process of cosmic alchemy takes time, billions of years of it. Yet, James Webb is finding heavy elements in galaxies that formed when the cosmos was still a cosmic infant, a time when such complexity should have been impossible. Picture a star as a cosmic kitchen. It starts with the simplest ingredients, hydrogen and helium, and slowly cooks them into heavier elements through the intense pressure and heat of nuclear fusion. Carbon, oxygen, silicon, iron, all these elements require multiple generations of stars to create and distribute. The very first stars, the primordial giants, had to live their entire, brilliant, violent lives, explode as supernovae, and seed the surrounding space with these newly forged heavy elements. Only then could the next generation of stars form, incorporating those elements into their own structure and into the planets that would orbit them. This stellar cooking process is like a cosmic assembly line that cannot be rushed. The most massive stars burn through their fuel quickly and explode within a few million years. But even this fastest of cosmic assembly lines needs hundreds of millions of years to produce significant amounts of heavy elements. The universe at 400 million years old simply had not had enough time for this process to work. Yet, spectroscopic analysis of these early galaxies, a technique that breaks light down into its constituent colors to reveal its chemical composition, shows clear signatures of oxygen, carbon, and even heavier elements like silicon and magnesium. The concentrations are not trace amounts that might be explained by a few unusually fast-burning stars. We are seeing metal abundances that suggest multiple generations of star formation and death had already occurred. A level of chemical enrichment that rivals much younger, more evolved systems. Dr. Emma Curtis Lake, who led some of these early spectroscopic observations, described finding galaxies with metallicities that were simply staggering. The spectral lines, the dark bands in the rainbow of starlight that correspond to specific elements, do not lie. These galaxies contain elements that should not exist in such quantities for billions more years of cosmic evolution. This discovery creates a cascade of problems for our cosmic timeline. If heavy elements existed this early, then planet formation could have begun much sooner than predicted. Rocky planets like Earth, which require these heavier elements to form, could have been a common feature of the very early universe. The implications for when and where life might have first appeared in the universe become staggering. Suddenly, the timeline for biology is pushed back billions of years into an era we once thought was barren and inhospitable. Some astronomers are proposing that the very first stars, the population 3 stars, might have been much more massive than we thought, burning through their lives and creating heavy elements at unprecedented rates. Others suggest that star formation itself might work differently in the early universe than it does today, with different efficiencies and different outcomes. But both of these explanations require us to revise fundamental assumptions about stellar physics. Assumptions that have been tested and confirmed for decades. The elements James Webb found should not exist yet, but they are there, written in the light of ancient galaxies, challenging everything we thought we knew about cosmic chemistry. What we discovered next makes the heavy element problem look simple by comparison. Imagine trying to build a skyscraper during an earthquake while blindfolded. That is what galaxy formation should have looked like in the early universe. The cosmos was violent, chaotic, and filled with dark matter and gas crashing together in random collisions. Galaxies should have grown slowly and messily through countless mergers over billions of years. What James Webb found instead were galaxies that looked as if they had been designed by a cosmic architect. The Hubble Space Telescope had already shown us that distant galaxies appear more irregular and chaotic than nearby ones. This made perfect sense. We were looking back in time to see galaxies in their awkward teenage years, still growing and organizing themselves. James Webb was supposed to push even further back, to see cosmic toddlers stumbling around in the dark. Instead, we found galaxies with clear spiral arms, organized central bulges, and structured star formation patterns. These features require delicate gravitational balance and billions of years of quiet, stable evolution to develop. In our own cosmic neighborhood, only the most mature, undisturbed galaxies display such perfect organization. Yet here they were, in the cosmic dawn, looking impossibly sophisticated. Dr. Stephen Finkelstein from the University of Texas described these discoveries as finding adult galaxies in a cosmic nursery. The level of organization defies everything we know about hierarchical structure formation, the theory that predicts small objects merge to form larger ones over cosmic time. These galaxies appear to have skipped their messy childhood entirely, emerging fully formed from the chaos of the early universe. The smooth, thin disk structures are particularly puzzling. In today's universe, galaxy disks form through a complex process where gas slowly settles into stable, rotating patterns over hundreds of millions of years. Early in cosmic history, Frequent mergers and chaotic gravitational conditions should prevent such delicate structures from forming or surviving. Yet, James Webb is showing us pristine spiral patterns that look as if they have never been disturbed, as if they have been spinning peacefully for eons. Even more mysterious are the central supermassive black holes that seem to be perfectly coordinated with their surrounding galaxies. In the modern universe, we observe tight correlations between the mass of a galaxy's central black hole and the properties of its host galaxy. This relationship takes billions of years to establish through a complex dance of feedback between star formation and black hole growth. Finding such coordination in young galaxies suggests processes we do not understand, a form of coevolution that happens almost instantaneously. The implications of this discovery challenge the entire concept of cosmic evolution. If galaxies can organize themselves this quickly, then our understanding of how structure forms in the universe needs a complete overhaul. It suggests that there is a hidden organizing principle at work, a force or a mechanism that we have not accounted for in our models. The smooth, organized galaxies James Webb discovered should not exist for billions more years, but their perfect spiral arms are just spinning us toward an even stranger discovery, about rotation speeds that appear to break the laws of physics. Galaxies rotate like cosmic hurricanes, vast, swirling systems of stars, gas, and dust held together by the gravitational embrace of dark matter halos that surround them like invisible cocoons. The faster a galaxy spins, the more mass it needs to prevent itself from flying apart. This fundamental relationship between rotation speed and mass is one of the most reliable and well-tested rules in astronomy. But James Webb found ancient galaxies spinning so fast they should have torn themselves to pieces billions of years ago. When astronomers measure how fast stars move in the disks of distant galaxies, they can calculate exactly how much total mass the galaxy contains. It is a simple application of physics, like watching cars on a circular racetrack. The faster they go without flying off the track, the steeper the banking of the road must be. In galaxies, that banking is provided by gravitational mass, mostly in the form of dark matter. The problem is that these early galaxies are rotating at speeds that require dark matter halos much more massive than anything our computer simulations of structure formation can produce. Some of these ancient galaxies are spinning at 300 kilometers per second, when they should be limited to perhaps 150. That is like finding a motorcycle taking a tight turn at twice the speed that should send it skidding into the wall. Dr. Claude-André Fauché-Giguère from Northwestern University has been studying these rotation curves and describes them as impossible under current models of galaxy formation. The dark matter halos required to stabilize such rapid rotation would be so massive that they should dominate the entire region of space around them. Yet, we do not see evidence for such monster halos in the structure of the cosmic web. Even stranger is how quickly these rapid rotation patterns must have established themselves. In today's universe, galaxy disks build up their rotation gradually as gas settles into stable orbits over hundreds of millions of years. But these ancient galaxies appear to have reached their maximum spin almost immediately after forming. It is like finding a figure skater already in a perfect, high-speed pirouette the moment they step onto the ice. The physics becomes even more problematic when you consider the conservation of angular momentum. As galaxies form from collapsing clouds of gas, they should spin up gradually as they shrink, just like a figure skater pulling in their arms. But the rotation speeds James Webb measured suggest these galaxies started with far more angular momentum than the cosmic web should have been able to provide. The initial conditions of the universe simply did not contain enough rotational energy to explain these observations. Some theorists are proposing exotic solutions, involving modified theories of gravity or alternative dark matter models that could provide the extra gravitational pull needed. Others suggest that early galaxy formation might involve processes we have never considered, like the transfer of angular momentum through cosmic magnetic fields. But every explanation requires abandoning well-tested physics or accepting that the early universe operated under a completely different set of rules. These impossibly fast-spinning galaxies are rotating us toward an even more disturbing discovery about collisions that happened before galaxies should have even had time to meet. Galaxy mergers are cosmic train wrecks that unfold over hundreds of millions of years. When two galaxies collide, their gravitational dance creates tidal tails, stellar streams, and distorted structures that astronomers can recognize like forensic evidence at a crime scene. James Webb found this evidence in galaxies that formed when the universe was so young that such collisions should not have been possible yet. The timeline problem here is severe. According to our models, the first galaxies were tiny, isolated islands of stars scattered across vast distances of empty space. They were like cosmic hermits, too far apart and too small to interact with each other in any significant way. Major galaxy mergers, the kind that dramatically reshape galaxies, should have waited until the universe was at least 1 billion years old, when cosmic structures had grown large enough and close enough to gravitationally influence each other. Yet, James Webb is showing us clear merger signatures in galaxies from just 400 million years after the Big Bang. We are seeing tidal streams of stars being pulled away from galactic cores, double nuclei that indicate recent collisions, and asymmetric, distorted structures that can only result from gravitational encounters between massive objects. Dr. Jehan Kartaltepe from the Rochester Institute of Technology has been analyzing these early merger signatures and describes them as finding car crashes in a world where cars have not been invented yet. The morphological features are unmistakable. These galaxies have definitely collided with other massive systems, but the cosmic timeline says such collisions should be impossible this early in universal history. The discovery gets even more puzzling when you consider the merger rates. In the local universe, major galaxy mergers are relatively rare events. A galaxy like the Milky Way might experience one significant merger every few billion years. But in these early observations, merger signatures appear in almost every massive galaxy James Webb examines. It is as if the young universe was experiencing a collision epidemic, a period of frantic, chaotic merging that our theories never predicted. Even more problematic is the scale of these ancient mergers. We are not seeing small galaxies absorbing tiny companions. These are major mergers between systems that are already massive and well-developed. The energy required to disrupt such large galaxies and then reorganize them into the structures we observe should take billions of years. Yet, we are seeing the aftermath when the universe was barely 500 million years old. The implications of this discovery cascade through our understanding of cosmic evolution. If major mergers were common this early, they would have triggered massive bursts of star formation and fed the central black holes at unprecedented rates. This should have left observable signatures throughout the universe, in the distribution of matter and the properties of the cosmic background radiation that we simply do not see. Some astronomers are beginning to question whether our fundamental timeline of structure formation is completely wrong. Maybe the universe organized itself much faster, much more violently, and much more efficiently than we ever imagined possible. But the evidence for impossible timing does not stop with galaxy collisions. Next, we discovered something even more fundamentally challenging about the cosmic microwave background itself. The cosmic microwave background, or CMB, is the universe's baby picture. It is a snapshot of what the cosmos looked like just 380,000 years after the Big Bang. A faint, ancient light that carries the imprint of the tiny density fluctuations that would eventually grow into galaxies, stars, and everything we see today. But James Webb's observations suggest that this baby picture might be telling us the wrong story about how the universe actually developed. The CMB shows us a universe that was remarkably smooth and uniform in its early days. The variations in density were incredibly small, just 1 part in 100,000. These tiny ripples in the cosmic fabric were the seeds that would slowly, over billions of years, grow through gravitational attraction into the vast, large-scale structures we observe today. Cosmologists have used sophisticated computer simulations to grow these seeds forward in time, predicting exactly what the universe should look like at any given epoch. These models are incredibly detailed, tracking how dark matter clumps together, how gas flows between galaxies, and how stars form within those galaxies. These simulations confidently predict that at the time James Webb is observing, galaxies should be small, irregular, and relatively rare. But that is not what we are seeing. The massive, organized galaxies that James Webb discovered require initial density fluctuations that were much larger than what the cosmic microwave background recorded. It is like finding full-grown trees in a field where the soil analysis says only grass seeds were planted. The numbers do not match. Dr. Rajendra Gupta from the University of Ottawa has been comparing James Webb observations with CMB predictions and describes the mismatch as fundamentally problematic. The early universe appears to have had far more structure-forming power than the baby picture suggests was possible. The discrepancy is not subtle. Some of the galaxies James Webb found are so massive that they require regions of space that were overdense by factors that the CMB says should not exist. The statistical probability of such massive galaxies forming from the observed initial conditions is essentially zero. We should not be seeing them, and yet we are. This creates a paradox that strikes at the heart of modern cosmology. Either our interpretation of the cosmic microwave background is wrong, or our understanding of how cosmic structures grow from initial fluctuations needs a complete revision. Both possibilities would require abandoning fundamental assumptions that have guided cosmology for half a century. Some theorists are exploring exotic solutions, involving things like primordial black holes that could have acted as seeds for early galaxy formation, or modified theories of gravity that could have accelerated the growth of structure. Others are beginning to suggest that the CMB might not be the pristine, untouched record of initial conditions we once thought it was. Perhaps later events in the universe's history have altered its properties in ways we do not yet understand. The mismatch between our cosmic baby picture and what James Webb actually found growing in the universe is pushing us toward an even more disturbing discovery about black holes that grew impossibly fast. Quasars are the universe's most powerful lighthouses. Brilliant, distant objects powered by supermassive black holes that consume matter at extraordinary rates and blast energy across billions of light years. These cosmic monsters contain millions, or even billions, of times the mass of our sun. But James Webb found fully grown quasars shining when the universe was so young that black holes should have barely begun their journey towards such enormous sizes. Building a supermassive black hole is like constructing a skyscraper, one grain of sand at a time. The process requires patience and a tremendous amount of raw material. Even under the most ideal conditions, black holes can only grow so fast because the very energy they release while feeding heats up and pushes away the matter they are trying to consume. This natural speed limit is a fundamental part of black hole physics. The physics is unforgiving. When matter falls into a black hole, it heats up and glows brightly in an accretion disk before disappearing forever. This intense radiation exerts an outward pressure, acting like a cosmic traffic cop that regulates how much material can approach the black hole at any given time. The maximum growth rate, known as the Eddington limit, means that even a black hole that starts with the mass of 1,000 suns would need over 1 billion years to reach the billion solar mass range. Yet, James Webb discovered quasars powered by billion solar mass black holes when the universe was only 600 million years old. These are not modest black holes still growing toward maturity. They are fully developed supermassive objects, already dominating their galactic environments and powering some of the brightest objects in the cosmos. Dr. Xiaohui Fan from the University of Arizona has been studying these early quasars and describes them as finding adult elephants in a nursery full of mice. The growth rates required to explain these observations exceed the theoretical limits by factors of 10 or more. Either our understanding of black hole physics is incomplete, or these black holes started out much larger than anything our models predict. The discovery becomes even more puzzling when you consider where these black holes came from originally. The very first black holes should have formed from the collapse of the first generation of stars, which themselves took tens of millions of years to form and evolve. This means the seed black holes that would eventually become supermassive should have started with masses equivalent to perhaps 100 suns at most. Getting from 100 solar masses to 1 billion solar masses in 600 million years, while respecting the Eddington limit, is mathematically impossible. It is like trying to drive from New York to Los Angeles in 1 hour while obeying the speed limit. Some theorists are proposing that the first black holes might have formed through completely different mechanisms, like the direct collapse of massive gas clouds, which could have created seed black holes with much larger initial masses. Others suggest that black hole growth in the early universe might not obey the same physical limits we observe today, perhaps through mergers or super Eddington accretion. But these impossibly massive black holes are not just growing. They are feeding star formation at rates that defy our understanding. Stars are born in cosmic nurseries called molecular clouds, where gravity slowly compresses gas and dust until nuclear fusion ignites. This process has natural speed limits built into the physics of how matter behaves under extreme conditions. But James Webb found galaxies forming stars at rates so fast they violate every theoretical maximum we have calculated for stellar birth. In today's universe, even the most active star-forming galaxies, known as starburst galaxies, convert only about 1% of their available gas into stars every million years. This efficiency limit exists because star formation is a messy, wasteful process. When massive stars form, they blow powerful stellar winds and eventually explode as supernovae, heating up and dispersing the surrounding gas. This stellar feedback acts like a cosmic thermostat, regulating how quickly new stars can form. The most extreme star-forming galaxies we observe today create about 1,000 new stars per year. This rate is already considered extraordinary and unsustainable. Galaxies forming stars. This quickly will exhaust their gas supplies within a few 100 million years. Yet, James Webb discovered early galaxies with star formation rates exceeding 10,000 stars per year, sustained over periods that should have been impossible. Dr. Pascal Oesch from the University of Geneva has been analyzing these stellar birth rates and describes them as finding cosmic factories running at 10 times their maximum rated capacity. The energy output from such intense star formation should heat up and expel all the remaining gas, shutting down further stellar birth almost immediately. Yet, these galaxies appear to maintain these extreme star formation rates for hundreds of millions of years. The physics becomes even more problematic when you consider the raw materials required. Forming 10,000 stars per year requires consuming gas at rates that would exhaust even the largest known reservoirs within a cosmic blink of an eye. These galaxies would need a constant resupply of fresh material from their surroundings. But the early universe was much less dense than today, making such massive gas flows unlikely. Even more puzzling is how these galaxies managed to retain their star-forming gas in the first place. The intense radiation from such rapid star formation should create powerful galactic winds that blow gas out of the galaxy entirely. We observe this process in local starbursts, where stellar feedback eventually quenches star formation. But these early galaxies seem to be immune to their own stellar violence, continuing to form stars at a furious pace. The discovery suggests that star formation in the early universe operated under a completely different set of rules than what we observe today. Maybe the primordial gas was denser and colder, allowing it to collapse more efficiently. Maybe the stellar feedback was less effective, or the entire process of stellar birth was fundamentally different when the cosmos was young. Some astronomers are proposing exotic mechanisms involving primordial gas with unusual properties or gravitational conditions that no longer exist in the modern universe. Others suggest that our understanding of stellar feedback and gas dynamics needs a major revision. But these impossible star formation rates are not happening in isolation. They are organizing themselves into structures that challenge our understanding of cosmic evolution itself. The early universe should have been a scene of cosmic chaos, a violent, turbulent place where matter crashed together randomly as gravity struggled to organize the aftermath of the Big Bang. Large-scale structure, the vast network of galaxies and voids that defines the modern cosmos, should have emerged slowly and messily over billions of years through countless random collisions and mergers. But James Webb found a level of cosmic organization that suggests the universe knew exactly what it was doing from the very beginning. Picture the cosmic web as a three-dimensional spider web stretching across billions of light years, with galaxies strung along filaments of dark matter like dewdrops on silk strands. This web structure is one of the most beautiful and organized features of the modern universe. Computer simulations show that it should take at least 1 billion years for such organized patterns to emerge from the smooth, uniform initial conditions after the Big Bang. Yet, James Webb is revealing hints of large-scale structure and organized galaxy distributions in the cosmic dawn. When the universe was only a few 100 million years old, we are seeing aligned galaxy clusters, coordinated star formation patterns across vast distances, and gravitational influences between objects that should still be isolated islands in space. Dr. Casey Papovich from Texas A&M University has been mapping these early large-scale structures and describes them as finding a completed jigsaw puzzle when you expected to see scattered pieces still looking for their places. The level of gravitational coordination between distant objects requires a cosmic web that developed far faster than our models predict. The organization appears at multiple scales simultaneously. Not only are individual galaxies more structured than we expected, but they are also organized into groups and clusters that should not have had time to form. The gravitational binding energy required to hold such systems together suggests they assembled much more quickly and efficiently than the theory of hierarchical structure formation allows. Even more mysterious is how these organized structures maintain their coherence across such vast distances. In the early universe, light had not had enough time to travel between widely separated regions, meaning they could not coordinate their behavior through any known physical mechanism. This is known as the horizon problem. Yet, we are seeing correlated properties, like star formation rates and galaxy orientations, across scales that should be causally disconnected. This cosmic organization problem strikes at the fundamental assumptions about how the universe evolved from smooth initial conditions to the structured cosmos we observe today. If large-scale structure formed this quickly, it suggests either that the initial conditions were not as smooth as we thought, or that there were processes at work that we do not understand. Some cosmologists are exploring ideas about cosmic phase transitions, primordial magnetic fields, or exotic forms of dark energy that could accelerate structure formation. Others are questioning whether the initial conditions after the Big Bang were as smooth and random as we have assumed. But this organized cosmic architecture is not just empty space. It is supporting planetary systems that seem to have formed impossibly early in cosmic history. Rocky planets like Earth require a cosmic recipe that takes billions of years to prepare. You need multiple generations of stars to forge heavy elements, supernova explosions to scatter those elements through space, and then the slow, patient process of gravitational accretion to gather dust and debris into solid worlds. But James Webb has found evidence of planetary systems in galaxies so young that the ingredients for rocky planets should not even exist yet. Planet formation is like cosmic cooking that cannot be rushed. The first stars contained only hydrogen and helium, the simplest elements forged in the Big Bang itself. Every heavier element, the carbon in our bodies, the oxygen we breathe, the silicon in Earth's rocks, the iron in our blood had to be manufactured inside the cores of stars and distributed by their explosive deaths. This process of element production takes time, even after heavy elements become available. Building planets is a slow process. Tiny dust grains must stick together to form pebbles. Pebbles must clump into boulders. Boulders must accumulate into asteroids. And asteroids must collide to build planets over tens of millions of years. The entire sequence, from the death of the first stars to the formation of the first rocky planets, typically requires at least 1 billion years of cosmic evolution. Yet, spectroscopic analysis of some early galaxies shows absorption features that could indicate the presence of dust and, potentially, even planetary debris in systems that formed when the universe was less than 800 million years old. Dr. Kevin Heng from the University of Bern describes these observations as finding evidence of planetary construction in a cosmic era when the building materials should not even exist. The implications of this discovery cascade through our understanding of when and where life might have first appeared in the universe. If rocky planets could form this early, then the conditions necessary for biology might have existed billions of years sooner than we ever imagined. The universe could have been teeming with potentially habitable worlds when our own solar system was still just a distant dream, an unformed cloud of gas and dust. Even more intriguing are the hints of atmospheric absorption in some of these early systems. While we cannot yet definitively confirm the presence of planetary atmospheres in such distant and ancient objects, the spectral signatures suggest the existence of complex chemistry involving heavy elements, arranged in ways that look suspiciously like atmospheric processes. The discovery forces us to reconsider how quickly planetary systems can assemble and begin operating as complex chemical laboratories. Maybe the process of dust grain sticking was more efficient in the early universe, or gravitational processes worked faster in the denser environment of cosmic youth. Some astronomers are proposing that the first planetary systems might have formed through mechanisms we do not observe in the modern universe, perhaps involving primordial materials or gravitational conditions that no longer exist today. But these rapidly forming planetary systems are not just an isolated puzzle. They are challenging our understanding of the cosmic inflation theory itself. Cosmic inflation theory proposes that the universe underwent a period of exponential expansion in the first fraction of a second after the Big Bang, stretching space faster than the speed of light and smoothing out any initial irregularities. This inflation should have created a universe with very specific, predictable properties, smooth on large scales, with tiny, precisely characterized fluctuations that would slowly grow into cosmic structure over billions of years. But James Webb's discoveries suggest the universe might not have followed the inflationary script at all. Inflation theory makes testable predictions about what the early universe should look like. The density fluctuations that eventually became galaxies should have specific statistical properties, following patterns that reflect the quantum mechanical processes that created them during the inflationary epoch. These fluctuations should be small, nearly scale invariant, and distributed according to precise mathematical relationships. The problem is that the massive, organized structures that James Webb discovered require initial fluctuations that were much larger and more organized than inflation predicts. The theory suggests that regions of space dense enough to form the observed massive galaxies should be extraordinarily rare, so rare that we should not see any in the cosmic volumes that James Webb can observe. Dr. Paul Steinhardt from Princeton University, one of the original architects of inflation theory, who later became one of its most prominent critics, describes these observations as potentially fatal problems for the inflationary paradigm. The statistical properties of the early galaxies do not match what inflation theory predicts should emerge from quantum fluctuations during a period of exponential expansion. Even more problematic is the coherent organization of structure across vast scales. Inflation theory predicts that different regions of space should have evolved independently after the rapid expansion separated them beyond any possible causal connection. Yet, James Webb's observations hint at coordinated properties and structures across distances that should be completely independent, according to inflationary cosmology. This discovery forces cosmologists to confront uncomfortable questions about whether cosmic inflation actually occurred, or whether it worked differently than our models suggest. Alternative theories that never required inflation are gaining renewed attention as potential explanations for James Webb's observations. Some theorists are exploring bouncing universe models, where our cosmos emerged from the collapse and rebound of a previous universe, potentially preserving organizational information that inflation would have erased. Others are investigating modified gravity theories or exotic forms of dark energy that could create the observed structure without requiring an inflationary expansion. The implications of this reach far beyond cosmology and into the realm of fundamental physics. Inflation theory has been intimately connected with our theories of quantum gravity and the earliest moments of cosmic history. If inflation is wrong, it suggests that our understanding of physics at the most fundamental level needs a major revision. But as multiple independent observations point to the same problems, the evidence becomes impossible to ignore. Science advances through the accumulation of evidence, and isolated anomalies can often be explained away by measurement errors, statistical flukes, or an incomplete understanding of the data. But when multiple, independent observations, using different techniques, all point to the same fundamental problem, the scientific community must confront the possibility that the accepted theories are simply wrong. James Webb's discoveries represent exactly this kind of converging evidence crisis. The telescope did not find just one type of anomaly. It discovered massive galaxies where small ones should exist, heavy elements that formed too quickly, organized structures that should be chaotic, rotation speeds that violate physics, collision signatures that predate possible interactions, star formation rates that break theoretical limits, and planetary systems that assembled impossibly fast. Each of these discoveries, taken alone, might be dismissed as an outlier or a statistical fluke, but together, they paint a consistent and deeply troubling picture of a universe that does not follow our rules. Independent research teams, using different analysis methods and looking at different regions of the sky, have confirmed these findings repeatedly. Dr. Labbé's galaxy mass measurements have been verified by multiple groups using completely different techniques. The spectroscopic evidence for early heavy elements has been detected in several independent surveys. The impossible rotation speeds have been confirmed through both direct velocity measurements and gravitational lensing studies. Even more compelling is how these diverse anomalies all point in the same direction, toward a universe that organized itself much faster and more efficiently than the standard Big Bang theory predicts. The problems are not random, scattered inconsistencies that might be explained by minor theoretical adjustments. They form a coherent and systematic pattern, suggesting that our fundamental timeline of cosmic evolution is wrong. The statistical weight of this accumulated evidence is becoming overwhelming. When astronomers calculate the probability that all of these observations could be explained by a combination of measurement errors or rare statistical fluctuations, the numbers become vanishingly small. We are not looking at a series of unlucky coincidences. We are seeing systematic discrepancies that demand a profound explanation. This convergence of evidence is forcing theoretical physicists to abandon incremental modifications to existing theories and begin to consider revolutionary alternatives. Dr. Subir Sarkar from Oxford University describes the situation as a paradigm crisis, a term used in the philosophy of science to describe a moment when accumulated anomalies can no longer be accommodated within the existing theoretical framework. The process mirrors historical scientific revolutions, where multiple, independent observations eventually forced a complete theoretical overhaul. just as the discovery of stellar parallax, galactic redshifts, and the cosmic microwave background converged to establish the Big Bang theory in the first place. James Webb's discoveries might be converging to overthrow it. Scientific institutions are beginning to acknowledge that these discrepancies require serious theoretical attention rather than ad hoc explanations. Major funding agencies are directing resources toward alternative cosmological models that could explain James Webb's observations without violating fundamental physics. The accumulated weight of evidence is pushing theoretical physicists toward completely new models of cosmic evolution. Behind closed doors in physics departments around the world, theorists are working frantically to develop alternative cosmological models that could explain James Webb's impossible observations without breaking the known laws of physics. These are not minor adjustments to existing theories. They are revolutionary new frameworks that could replace the Big Bang theory entirely. The quiet urgency of this theoretical work reflects how seriously physicists are taking the mounting evidence crisis. Dr. Neil Turok from the Perimeter Institute has been developing cyclic cosmology models, where the universe undergoes infinite cycles of expansion and contraction, with each cycle preserving organizational information that could explain the rapid structure formation James Webb observed. These models suggest our universe might not have had a beginning at all, but rather emerged from the organized collapse of a previous cosmic cycle. Meanwhile, Dr. João Magejo from Imperial College London is exploring variable speed of light cosmologies, where the fundamental constants of physics, like the speed of light, were different in the early universe. If light traveled faster in cosmic youth, it could allow widely separated regions of space to coordinate their evolution, explaining the large-scale organization James Webb discovered without requiring impossible timescales. Modified gravity theorists like Dr. Sabine Hossenfelder are investigating whether gravitational physics itself works differently on cosmic scales or in extreme environments. If gravity was stronger or operated through additional dimensions in the early universe, structure formation could proceed much faster than general relativity predicts, naturally explaining the mature galaxies James Webb found. Even more radical are theories involving multiple universes or higher dimensional physics. Some models suggest our observable cosmos might be embedded in a larger multiverse structure, with matter and energy flowing between connected regions through mechanisms we do not yet understand. These scenarios could provide the additional organizational power needed to explain rapid cosmic evolution. Dr. Paul Frampton from the University of North Carolina has been exploring bouncing cosmologies, where dark energy cycles between expansion and contraction phases, creating periods of accelerated structure formation that could explain James Webb's observations. These models abandon the idea of a single Big Bang in favor of multiple cosmic epochs with different physical properties. The theoretical work is proceeding with unusual urgency because the observational evidence continues to mount faster than explanations can be developed. Each new James Webb discovery adds further constraints that eliminate more traditional explanations, forcing theorists toward increasingly exotic alternatives. What makes this theoretical revolution particularly significant is how it is happening across multiple subdisciplines simultaneously. Cosmologists are revising their models of cosmic evolution. Particle physicists are questioning our understanding of fundamental constants. And astrophysicists are reconsidering the processes of stellar and galactic formation. The James Webb crisis is forcing a coordinated rethinking of physics itself. Some of the most promising new models involve what physicists call emergent gravity. The idea that gravitational attraction might not be a fundamental force, but rather an emergent property arising from more basic quantum mechanical processes. If gravity works differently than we thought, it could explain why cosmic structures form so much faster than our current theories predict. But these new theoretical frameworks are approaching a tipping point, where they might fundamentally change our understanding of time and space itself. Einstein's theory of relativity taught us that space and time are woven together into a single, unified fabric called space-time, which can be stretched, warped, and curved by the presence of matter and energy. This profound understanding has been tested countless times and forms the very foundation of modern cosmology. But James Webb's discoveries are forcing physicists to question whether space-time itself might work differently than we have assumed, especially in the extreme conditions of the early universe. The problem is not just that galaxies formed faster than expected. It is that they formed in ways that seem to violate the principle of causality itself. Structure formation requires information to travel between different regions of space so they can coordinate their gravitational behavior. But in the early universe, many of the organized structures James Webb discovered are separated by distances that light had not had time to cross, making such coordination impossible under our current understanding of space-time. Dr. Lee Smolin from the Perimeter Institute has been exploring theories where time itself might be an emergent property, rather than a fundamental aspect of reality. In these models, what we experience as the flow of time could be an approximate description that breaks down under the extreme conditions of the early universe. If time worked differently, it could allow for processes that seem impossible under our current physics. Even more radical are theories suggesting that space might have additional, hidden dimensions that were accessible in the universe's youth, but became curled up and hidden as the universe evolved. These extra-dimensional models could provide pathways for information and energy to travel faster than the speed of light in our familiar three-dimensional space, explaining the impossible coordination James Webb observed. Some physicists are even investigating whether the speed of light itself might not be a constant throughout cosmic history. If light traveled faster in the early universe, it would allow widely separated regions to communicate and coordinate their evolution, naturally explaining the large-scale organization that formed too quickly under our current physics. Dr. Carlo Rovelli from the French National Center for Scientific Research has developed loop quantum gravity theories, where space-time itself is quantized, made up of discrete, indivisible units rather than being a continuous fabric. In these models, the very fabric of space-time might behave in strange and unpredictable ways under the extreme conditions of the early universe, allowing for structure formation processes that are impossible in the smooth, continuous space-time of classical physics. The implications of these ideas reach far beyond cosmology and into the very nature of reality itself. If our understanding of time and space is fundamentally wrong, it affects everything from the foundations of quantum mechanics to the possibility of time travel. The James Webb discoveries might be showing us that the universe operates according to a deeper level of physics that we have not yet discovered. These space-time theories are all converging on a single, disturbing possibility that the Big Bang might not have been the beginning of everything after all. For nearly a century, the Big Bang has been more than just a scientific theory. It has been our culture's origin story, the ultimate answer to the profound question of where everything came from. But James Webb's discoveries are forcing us to confront the possibility that the Big Bang might not have been the beginning of everything, but rather just one event in a much larger, much older cosmic story that we are only now beginning to understand. The evidence is pointing toward a universe that was already organized and structured when the event we call the Big Bang occurred. The massive galaxies, the early heavy elements, and the coordinated large-scale structures that James Webb discovered all suggest that cosmic evolution did not start from a smooth, uniform, and simple beginning. Instead, they hint at a universe that inherited its organizational information from whatever came before. Dr. Anna Ijas from New York University has been developing models where the Big Bang emerges from the collapse and bounce of a previous universe. In these scenarios, the organized structures that James Webb observed could be the fossilized remnants of cosmic evolution that preceded our current phase of expansion. The universe might undergo infinite cycles of expansion, contraction, and rebirth, with each cycle preserving and building upon the information from the previous one. Even more revolutionary are theories suggesting that multiple universes might exist simultaneously, with matter and energy flowing between them through mechanisms we do not yet understand. If our observable cosmos is connected to a larger multiverse, it could explain where the organizational power for such rapid structure formation came from. It was simply borrowed from neighboring universes. Some physicists are exploring the possibility that the Big Bang was actually a phase transition rather than a creation event, just as water can transition from ice to liquid to vapor while remaining the same fundamental substance. The universe might have transitioned from one physical state to another without actually beginning to exist. Dr. Abhay Ashtekar from Pennsylvania State University has developed loop quantum cosmology models where the Big Bang singularity is replaced by a big bounce, a transition from a contracting phase of cosmic evolution to our current expanding phase. In these models, the universe has no beginning and no end, but rather undergoes eternal cycles of expansion and contraction. The philosophical implications are staggering. If the Big Bang was not the beginning, then questions about what came before it become scientifically meaningful rather than just metaphysical speculation. The universe might be infinitely old, with our current expansion phase being just one chapter in an eternal story. This possibility challenges not just our cosmology, but our entire understanding of causation, existence, and the nature of reality itself. If the universe has always existed in some form, it changes how we think about everything, from the origins of the physical laws to the possibility of life having existed in previous cosmic cycles. The James Webb discoveries might be showing us that we are not the first chapter of cosmic evolution, but rather the latest chapter in an infinite book. The scientific revolution brewing in cosmology is not just about adjusting details or fine-tuning existing theories. James Webb's discoveries are approaching a critical threshold where the accumulated evidence might force the complete abandonment of our current cosmic origin story in favor of something entirely different. We are standing at the edge of a paradigm shift that could rival the Copernican revolution in its scope and its implications for human thought. The tipping point in science comes when anomalies can no longer be explained by modifying existing theories. In the history of science, this moment arrives when multiple, independent lines of evidence all converge on the same conclusion that the fundamental assumptions underlying the accepted theory are simply wrong. The James Webb discoveries are rapidly approaching this critical mass of contradictory evidence. Dr. Subir Sarkar from Oxford University describes the current situation as a crisis of epic proportions in cosmology. The standard model of cosmic evolution requires increasingly exotic and elaborate modifications to accommodate each new James Webb observation. Dark energy must be more complex. Dark matter must behave differently. Inflation must work in ways we never imagined. And stellar physics must operate under a completely different set of rules in the early universe. The mathematical contortions required to save the Big Bang theory are becoming so elaborate that many physicists are questioning whether it is time to abandon the theory entirely, rather than continue patching it with increasingly implausible modifications. It is reaching the point where the cure is becoming worse than the disease. Major scientific institutions are beginning to acknowledge the severity of the crisis. The European Space Agency has approved funding for missions specifically designed to test alternative cosmological models. The National Science Foundation in the United States has created new funding categories for research into non-standard cosmologies. These institutional responses reflect a growing recognition that the James Webb discoveries represent more than just interesting anomalies. The convergence of evidence is accelerating. Every few months, new James Webb observations add to the pile of inexplicable data. The statistical probability that all these anomalies could be explained by measurement errors or theoretical oversights is approaching zero. The universe that James Webb is revealing simply does not match the universe that our theories predict. Historical precedent suggests that we are approaching the moment when the scientific community will be forced to choose between increasingly implausible explanations for the existing theory and revolutionary new models that naturally explain the observations. The geocentric Ptolemaic system of planetary motion required increasingly complex epicycles to match observations, until Copernicus proposed that the Sun, not the Earth, was the center of the solar system. We might be witnessing a similar moment in cosmology. The Big Bang Theory is requiring increasingly complex modifications to match James Webb's observations. Alternative theories that seemed radical just a few years ago are beginning to look like natural and elegant explanations for what we are actually seeing. The next few years of James Webb observations will likely determine whether we are looking at the end of the Big Bang era in cosmology and the beginning of something completely new. The story of how the universe began is not just a scientific theory, it is the foundation of how we understand our place in existence itself. If James Webb's discoveries force us to abandon the Big Bang Theory and embrace a completely different cosmic origin story, the implications will cascade through every aspect of human knowledge, from philosophy and religion to our most basic sense of meaning and purpose. Throughout history, changes in our cosmic story have triggered profound shifts in human consciousness. When Copernicus showed that the Earth was not the center of the universe, it did not just change astronomy. It revolutionized philosophy, religion, and humanity's sense of its own importance. When Darwin revealed that life evolved through natural selection rather than being specially created, it transformed not just biology, but our entire understanding of what it means to be human. The James Webb revolution promises to be even more fundamental. If the universe has always existed in some form, with no ultimate beginning, it challenges our most basic assumptions about causation, creation, and the nature of existence itself. The questions that have driven human inquiry for millennia. Why is there something rather than nothing? What came before the beginning? What is our cosmic purpose would need to be completely reframed. Dr. Carlo Rovelli, from the French National Center for Scientific Research, argues that major scientific revolutions always force us to reconstruct our understanding of reality from the ground up. The James Webb discoveries are not just challenging cosmology, they are challenging the conceptual frameworks we use to understand existence itself. If the universe operates according to a level of physics we have not yet discovered, with time and space working differently than we have assumed, it opens up possibilities we can barely imagine. Maybe consciousness plays a fundamental role in cosmic evolution. Maybe information is more fundamental than matter and energy. Maybe the universe is stranger and more wonderful than our current theories even allow us to suggest. The implications extend to the possibility of life itself. If rocky planets and complex chemistry emerged billions of years earlier than we previously thought, the universe might have been teeming with life when our own solar system was still just a distant possibility. We might not be among the first intelligent beings to contemplate the cosmos, but rather the latest in an unimaginably long chain of cosmic evolution. Even our understanding of death and time could be transformed. If the universe undergoes eternal cycles of expansion and contraction, with information being preserved across these cosmic phases, it raises profound questions about whether anything is ever truly lost. The James Webb discoveries might be showing us a universe where existence itself is eternal and indestructible. The psychological adjustment to a completely new cosmic story will be challenging. Humans have always needed origin stories to provide meaning and context for their lives. The Big Bang Theory, for all its scientific precision, also served as a modern creation myth that helped people understand their place in the cosmos. But perhaps the most profound implication is that the James Webb discoveries remind us of how much we still do not know. The universe continues to surprise us, revealing new mysteries just when we thought we had everything figured out. The greatest discovery might not be any specific new theory, but rather the humbling recognition that the cosmos is far stranger, more complex, and more wonderful than we ever imagined. The The James Webb Space Telescope was built to confirm our understanding of cosmic origins. Instead, it might be showing us that the greatest adventures in understanding are still ahead of us, waiting to be discovered in the infinite mystery of existence itself. We set out to prove our cosmic origin story with the most powerful telescope ever built, expecting to find confirmation of everything we thought we knew about the universe. Instead, James Webb showed us galaxies that should not exist, stars that formed too quickly, and structures too organized for a universe in its youth. The telescope that was meant to be the ultimate witness to the Big Bang might instead be writing its obituary. The evidence is overwhelming and undeniable. Massive galaxies in the cosmic infancy, heavy elements that formed impossibly fast, rotation speeds that break the laws of physics, collision signatures that predate possible interactions, star formation rates beyond all theoretical limits, and planetary systems that assembled before their ingredients should have even existed. Each of these discoveries, taken alone, might be explained away, but together, they paint a consistent and damning picture of a universe that refuses to follow our rules. This is not just a crisis in cosmology. It is a revolution in our understanding of reality itself. The accumulated weight of James Webb's observations is forcing physicists to question not just when the universe began, but whether it had a beginning at all. We might be witnessing the end of the Big Bang era and the birth of a completely new cosmic story. The implications cascade through every aspect of human knowledge. If time and space work differently than we have assumed, if the universe has always existed in some form, if cosmic evolution operates according to a level of physics we have not yet discovered, then everything we thought we knew about existence needs to be reconsidered. The questions that have driven human inquiry for millennia must be completely reframed. But perhaps the most profound discovery is how much mystery remains. The universe continues to surprise us, revealing new wonders just when we thought we had everything figured out. The James Webb observations remind us that the cosmos is far stranger, more complex, and more wonderful than our theories suggest. The greatest scientific revolutions in history began with observations that did not fit the existing theories. Copernicus, Darwin, Einstein all started with pieces of evidence that forced humanity to reconstruct its understanding of reality from the ground up. The James Webb discoveries might represent the beginning of a similar revolution, one that will transform not just cosmology, but our entire conception of existence itself. We stand at the threshold of a new cosmic story, one that might reveal the universe to be eternal, infinite, and far more mysterious than we ever imagined. The telescope that was built to confirm our origin story might instead be opening the first chapter of an entirely new book of cosmic understanding. The greatest adventures in discovery are not behind us. They are waiting to be written in the light of ancient galaxies that refuse to follow our rules, in the spin of impossible stars, and in the organization of a universe that seems to have known exactly what it was doing from the very beginning. The story of how the universe came to be is not ending. It is just beginning to be told.
Imagine you are drifting weightlessly in the silence of space. There is no up or down, only a void stretched infinitely in all directions, peppered with distant lights. Around you, silence presses in, the kind of silence that feels eternal. The cold is not just a temperature, it is an absolute, penetrating stillness that seeps into every atom of your being. And before you, from the emptiness, something begins to emerge. A world that defies understanding, a planet with oceans of molten diamonds and iron rains falling through dense, exotic atmospheres. These are not the settings of dreams or science fiction. They are real, and they are out there. The universe, in all its unimaginable scope, is home to worlds more alien than we could have dared to imagine. Planets where a single day outlasts a year. Planets where the skies are black, not from the absence of light, but because their atmospheres are so crushingly dense that no sunlight ever reaches the surface. Giant planets with endless storms that have raged since long before human history began. Places that echo Earth just enough to stir longing and fear. Why are these strange, distant worlds so important to us? Why do we feel drawn to them, as if searching for a cosmic mirror in which we might see our own reflection? Perhaps it's because in understanding them, we inch closer to answering the most profound question we can ask. Are we alone? If you've ever found peace in the quiet of the stars or sought comfort in the idea that the universe is vaster than our troubles, then you belong here. Join us as we journey through the cosmos. Subscribe, support, and become part of our celestial family. Your presence helps us keep the flame of curiosity burning through the long nights, bringing knowledge and peace to every restless soul beneath the stars. Look up at the night sky. Each twinkling star might be a sun. Each sun might have its own family of planets. Each planet a story yet untold. The creation of those worlds begins in the deep, cold emptiness between the stars. There, colossal clouds of interstellar dust and gas drift quietly until something changes. Gravity stirs, a whisper becomes a roar, the cloud collapses inward, heating up, compressing, igniting. A star is born. Around this newborn sun, leftover gas and dust begin to spin in a flat, swirling disk. Over millions of years, this protoplanetary disk becomes the cradle of planets. Microscopic grains of dust collide and stick. Pebbles form, then boulders, then mountain-sized chunks, planetesimals. These ancient building blocks collide, fuse, and grow, each collision a violent act of creation. Slowly, worlds emerge. Near the star, only metal and rock can survive the blistering heat, forming small, dense planets like Mercury, Venus, Earth, and Mars. Farther out, where it's cold enough, ices and gases join the mix, giving rise to giant worlds like Jupiter and Saturn, and icy giants like Uranus and Neptune. This architectural layout, rocky inner worlds, gaseous outer giants, is just one blueprint. The cosmos holds infinite variations. Some planetary systems are chaotic tangles of giants huddled close to their stars. Others have planets dancing between two suns, caught in elegant gravitational ballets. Some systems expel planets into the void, creating rogue worlds wandering alone through the darkness. With every telescope, every mission, we reveal more, planets of such strangeness they rewrite what we thought we knew. Scorching gas giants hugging their stars, rocky worlds that spin backwards, and moons that may harbor oceans hidden beneath ice. Our own solar system is just a whisper in a chorus of voices. Now, imagine those primordial clouds again, those slow, patient architects of stars and planets. Somewhere right now, in the shadows of a distant galaxy, dust is becoming stone, stone is becoming world. Maybe it will be barren, maybe it will bloom. Maybe one day beings will look up from its surface, their eyes filled with wonder, and ask the same question we ask under our stars. Are we alone? Beyond the pale light of Mercury and the violent pressure of Venus, we arrive at a place unlike any other, our home, Earth. Suspended in darkness, glows with a serene blue brilliance. It is a fragile sphere of life wrapped in a thin veil of atmosphere, rotating quietly in the warmth of a yellow star. From space, it seems peaceful, but hidden within its clouds, oceans, and lands is a complexity that has taken billions of years to sculpt. Here, water flows freely across continents, surges in tides, evaporates into vapor, and rains back onto soil and rock. Earth is an orchestrated balance of forces, geological, chemical, biological. Its atmosphere just thick enough to shield life from cosmic radiation, yet thin enough to let sunlight in is composed with a precision that makes life possible. With 21% oxygen, 78% nitrogen, and traces of carbon dioxide, it is both a protective skin and a living system. The planet's magnetic field, born from the dynamo motion in its liquid iron core, acts as a guardian, deflecting solar wind and cosmic rays. Without this invisible shield, Earth's surface would be stripped bare like the moon. But it is not just protection that the magnetic field offers. It also reveals itself through beauty-dancing auroras of green and violet over polar skies, silent, ethereal, and electric. Our moon, a companion formed in a cataclysmic collision, helps stabilize Earth's rotation. Its gravitational pull orchestrates the tides, stirring the oceans in cycles that may have played a crucial role in the emergence of life. No other planet in our solar system has a satellite so large in proportion to its host, a cosmic coincidence, or a stroke of design from the hand of chance. And then there is Earth's geological life. Tectonic plates slide over molten currents, shaping continents, birthing mountains, and pulling ocean floors beneath land in an endless recycling of the crust. Volcanic eruptions and earthquakes are not anomalies, but symptoms of Earth's living geology. This motion helps regulate the carbon cycle, a planetary breath that stabilizes the climate over millennia. But perhaps most striking of all is the fact that Earth is covered by oceans. More than 70% of the surface is water. And in this water, in tide pools, thermal vents, and shallow seas, life began. Single cells evolved into colonies, then organisms, and eventually creatures that breathe, walk, think, and wonder. Evolution, powered by sunlight and time, gave rise to consciousness and eventually to us. From Earth's surface, our gaze turns outward again, to Mars, the red planet. Its surface, seen through telescopic eyes, hints at a turbulent past. Great canyons slash the planet's crust. Extinct volcanoes reach skyward. Dry riverbeds trace the ghosts of ancient water. Once, perhaps, Mars was not so different from Earth. Mars is a cold, arid place now. Its atmosphere is thin, only 1% of the pressure of Earth's, and composed mostly of carbon dioxide. Yet there is water, frozen in the poles, perhaps hidden in underground aquifers. And there is time. A Martian day is just 40 minutes longer than ours, and its seasons, though harsher, follow a familiar rhythm. Billions of years ago, Mars had a thicker atmosphere and liquid water on its surface. Rovers have traced the pathways of rivers, the shores of lakes. Sedimentary layers tell stories written by flowing water and wind. What happened? Mars lacks a magnetic field to shield it. The solar wind stripped away its atmosphere, and with it, its warmth and water. Yet it is not a dead world, far from it. Beneath its surface, some scientists believe microbial life may still hide, safe from ultraviolet rays and cosmic radiation. The search for that life is one of humanity's great scientific quests. If we find life on Mars, even the simplest form, it will mean that life is not a miracle confined to Earth. It will mean the universe teems with potential. But Mars is not just a scientific target, it is a destination. Elon Musk dreams of colonizing it. NASA plans human missions. The challenges are immense radiation, low gravity, psychological isolation. But the goal is clear: to become a multi-planetary species. If we can survive and thrive on Mars, it will mark the first great leap into a future among the stars. And still, as we venture outward, we look back. Earth is warm and blue. Mars is cold and red. Two neighboring planets, once perhaps alike, now separated by a cosmic fork in the road. One cradles life, the other bears its fossilized shadows. The contrast is a reminder of how delicate the thread of habitability truly is. Approaching Jupiter is like nearing a living storm the size of eternity. Its stripes are not just color, they are atmospheric rivers moving at hundreds of kilometers per hour. each band a distinct climate zone locked in battle with its neighbors. And there, nestled among the roiling chaos, is the Great Red Spot, a cyclone so vast that 3 Earths could vanish inside it. It has raged for centuries, an ancient scar in the fabric of the sky. Jupiter is not merely a planet, it is a system unto itself. With more than 90 known moons, it is a miniature solar system within our own. Some of these moons are among the most fascinating bodies in the cosmos. Ganymede, the largest moon in the solar system, is even bigger than Mercury and has its own magnetic field. Europa, smooth and pale, hides a subsurface ocean beneath its icy crust, an ocean that may harbor life. Volcanic Io, constantly reshaped by the tidal forces of Jupiter's gravity, is the most geologically active place we know. The sheer gravitational dominance of Jupiter helped shape the entire solar system. It may have flung countless comets and asteroids toward the inner planets, delivering water to Earth or perhaps posing deadly threats to early life. Its presence is both protector and destroyer, guardian and tyrant. And then there's Saturn, further out but no less majestic. If Jupiter is power, Saturn is grace. Its rings, seen from afar, are impossibly thin, made of ice and rock and dust, suspended in a silent ballet. Each particle in those rings follows its own orbit, yet together they create something luminous and ethereal. They are the most delicate structures on a planetary scale, a cosmic lacework 100,000 kilometers across, but only a few dozen meters thick. Saturn, too, has moons worth marveling over. Titan, with its thick, nitrogen-rich atmosphere, has lakes of methane and ethane. It rains there, but not water. A methane cycle mirrors Earth's hydrological one, making Titan a frozen analog of our planet. Beneath its crust, like Europa, may lie a hidden ocean. And then there's Enceladus, a tiny moon that shoots plumes of water vapor into space, suggesting a subsurface sea kept warm by tidal forces. We have flown through those plumes. We have tasted the ocean of another world. The outer planets, Uranus and Neptune, are stranger still. Tilted on its side, Uranus rolls through space like a barrel, its seasons extreme and long. Its atmosphere, a mix of hydrogen, helium, and methane, gives it a ghostly cyan hue. Neptune, deep blue and distant, hosts the fastest winds in the solar system, up to 2,000 kilometers per hour. It is a frozen fury at the edge of sunlight's reach. These planets and moons are not only physical worlds, they are emotional metaphors. Jupiter is the patriarch, Saturn the archivist, Uranus the exile, Neptune the dreamer. They remind us that every place, no matter how distant, carries a story, and that our own story is richer for knowing theirs. Beyond Neptune lies the Kuiper Belt, home to Pluto and countless icy bodies. Once a planet, now a dwarf, Pluto revealed its heart to us literally when New Horizons flew past and captured that now iconic image, a frozen plain in the shape of a heart, made of nitrogen ice. It is a world of mountains, glaciers, and complex geology, not dead, not simple, just far. The solar system does not end there. The Oort cloud, a spherical shell of icy debris, marks the boundary of the sun's gravitational dominion. Some of its objects take millions of years to orbit once. It is from here that long-period comets arrive, intruding into the inner solar system like messengers from the dark. These places, Jupiter, Saturn, Uranus, Neptune, Pluto, remind us of scale, of time, of complexity beyond imagination. They challenge our notion of habitability, of what is alive, of what can be known. Each world is a possibility, each moon a mystery, and somewhere among them, perhaps in a warm ocean beneath ice, or in a cave shielded from radiation, there is life. Simple, silent, surviving, or maybe not. Maybe we are alone. But whether life is out there or not, These distant orbs change us. To see them, to name them, to visit them, is to understand ourselves better. We are not confined to one world. We are not prisoners of gravity. We are explorers, dreamers, makers of meaning from rock and gas and light. And now we turn our eyes outward again, past the sun's final breath, past the frontier of our solar system, toward the stars. Between our solar system and the next, there is no road, no air, no landmarks, only distance measured not in kilometers or miles, but in time and silence. This is the interstellar medium, a vast, thin haze of gas and dust and fields that stretches for light years in every direction. It is neither empty nor welcoming. It is the space between homes. To travel here is to confront isolation on a scale unimaginable. Voyager 1, launched in 1977, now coasts through this void. It carries with it a golden record images, sounds, greetings, our planetary message in a bottle, but no one has yet replied, and maybe no one ever will. Beyond the heliopause, where the solar wind yields to interstellar pressure, the physics changes. Particles move differently. Fields behave oddly. This region, once purely theoretical, is now partially mapped thanks to probes like Voyager. Still, we have only dipped a toe into the cosmic ocean. The stars we see twinkling overhead are still impossibly far. The nearest is Proxima Centauri, just over 4 light-years away. At the speed of the fastest spacecraft we've built, it would take over 70,000 years to get there, yet we dream of reaching it. Proxima b, a potentially habitable planet in that system, has ignited hopes of another Earth. But even the most optimistic missions like Breakthrough Starshot, which proposes sending gram-scale probes at 20% the speed of light, remain decades from realization. Still, the physics of such travel stirs imagination. Concepts like light sails, fusion propulsion, antimatter drives, and even warp bubbles stretch the boundary between science and speculation. Some of these may prove viable, others may remain beautiful ideas, but each is a step toward breaking the tyranny of distance. Beyond technology, interstellar travel demands a transformation of thought. To cross between stars is to leave behind everything familiar, not only home and light and time, but even language. The vastness is humbling. It reshapes questions of survival, society, and self. Could we remain human scattered across such gulfs? Would a generation ship preserve culture or birth something new entirely? The philosophical weight is enormous. To voyage outward is not only a technical act, it is a moral one. It forces us to ask why we go, what we carry, what we leave behind. It turns space into a mirror. And then there is the quiet, the cosmic background hum, the echo of the Big Bang permeates all. It is not sound in the usual sense. There is no air to carry vibration, but a whisper of radiation, uniform, omnipresent, a fossil from when the universe was just 380,000 years old. To measure it is to look backward in time, to a moment when atoms were first able to form and light was finally free to travel. The background radiation is smooth, but not perfectly so. Tiny fluctuations, mapped in exquisite detail by satellites, tell us about the early universe's density, temperature, and shape. These are the fingerprints of inflation, an era when the universe expanded faster than the speed of light. This expansion smoothed the cosmos, made it flat, and planted the seeds of all structure. Inflation, still theoretical but well supported by data, changed everything. It answers puzzles that once confounded cosmologists: why the universe is so homogeneous, why its geometry is flat, why there are no magnetic monopoles. But it raises new questions, too. What drove inflation? What ended it? And could it still be happening elsewhere? Some theorists propose eternal inflation. In this view, our universe is just one bubble in an infinite foam, each bubble a separate cosmos with its own laws and constants. This multiverse, as strange as it sounds, may be a consequence of high-energy physics. It could explain why our universe is so finely tuned for life, not because it was meant to be, but because we happen to be in a bubble where life is possible. These are not idle speculations. They emerge from equations, from observations, from the clash of quantum mechanics and general relativity, yet they point beyond science. They edge toward meaning. To imagine other universes is to expand our definition of reality, to accept that what we see, the stars, the galaxies, the void, is only a fraction of all that exists. And perhaps, just perhaps, that there are other versions of ourselves, living other lives in places that will forever remain beyond reach. Still, our focus returns, not to what might be, but to what is. The interstellar medium, the cosmic microwave background, the physics of voids and fields, these are not merely abstract. They are the canvas on which our story is painted. And through this canvas, something else moves. A ripple, a wave, not of light, but of gravity itself. Shall we listen to it? The dance of existence continues in silence beyond the cosmic horizon. All that has come before black holes, dark matter, exoplanets finds a home in a universe that is still expanding, still evolving. But beyond the phenomena we observe, the deepest questions begin. What gave rise to this universe, and why these laws, these constants, this balance that allows complexity, life, and awareness? In the first trillionths of a second after the Big Bang, something extraordinary happened. Not the explosion itself that's a metaphor, but the rapid swelling of space itself. Inflation, a period when the universe ballooned faster than light, driven by a mysterious energy embedded in the quantum vacuum. During this brief era, quantum fluctuations, microscopic wrinkles in the energy field, were stretched to cosmic scales. They became the seeds of all future galaxies, all future us. These primordial ripples are imprinted in the oldest light. We can detect the cosmic microwave background. It shows us tiny variations in temperature, barely 1 part in 100,000. But those tiny differences determine the shape of the universe to come. Regions slightly denser than average drew more matter, forming stars, clusters, and vast cosmic filaments. The great web of the universe began as a trembling in a quantum field, and this is where theory brushes against the edge of the unknowable. Inflation may not have been a one-time event. Some physicists propose eternal inflation, a bubbling cosmos where each bubble is a universe, our universe, then is one among an infinite multiverse. Each bubble may have different physical laws, different particles, even different dimensions. Perhaps, in one, stars never formed. In another, time runs backward. In another, life is silicon, not carbon. These ideas are not just speculative dreams. They emerge from the math that governs the quantum and cosmological realms. String theory, for instance, suggests a universe with 10 or more dimensions, most curled up tightly, beyond our detection. It offers a framework where gravity and quantum mechanics can finally merge. But even if these theories are right, how could we ever test them? What would it mean to peer beyond our cosmic bubble? Could gravitational waves from other universes leave a scar in our sky? Could high-energy particles from a neighboring cosmos punch through the veil? Scientists seek signatures in the sky, unusual cold spots, unexpected alignments, anomalies in the cosmic background that might hint at collisions with other universes. And still, the question deepens. Why is there something rather than nothing? Why these laws, this geometry, this dance of energy and entropy? The anthropic principle suggests we live in a universe compatible with our existence. Others might be barren, short-lived, or chaotic. But this is not a satisfying answer. It begs for more. It hungers for insight. Philosophers and physicists converge here. Some suggest the universe is a mathematical structure, existing because mathematics is inevitable. Others imagine a self-creating cosmos, one that brings itself into being through a loop of quantum cause and effect. Still others invoke the simulation hypothesis that all of this, from quarks to quasars, is information processed in some vast computational substrate. No matter the answer, the search itself is sacred. And so we push forward. We build better telescopes. We refine our theories. We teach our machines to sift patterns from noise. We test the edge of what is knowable. Yet in the midst of this cosmic ambition, we return to something deeply human. The awe of seeing a sunrise. The touch of a child's hand. The memory of a loved one. These, too, are part of the universe. No less fundamental. No less cosmic. The neutrinos passing through your body right now were forged in stellar cores and supernovae. The calcium in your bones, the iron in your blood, the oxygen you breathe, all made in ancient stars. You are not just in the universe, you are of it. A way for the matter to become self-aware, to dream. And dream we must, of life beyond Earth, of civilizations rising among exoplanets, of technologies that fold space, of messages carried not by light, but by gravitational whispers. The Voyager probes, launched in the 1970s, now drift through interstellar space, carrying golden records etched with music and greetings from Earth. They are tiny ambassadors, drifting farther from us each year, but also closer to eternity. We will go further with light sails, fusion drives, and maybe someday wormholes. We will seed new worlds, if not with our bodies, then with our minds, our machines, our stories. Perhaps the universe's greatest mystery is not why it exists, but why it allows for beings who can ask why, beings who can fall in love, grieve, create symphonies, and build particle accelerators.
You are not merely floating in space. You are suspended on a membrane of perception. Behind you lies the echo of human history, a chorus of myths, physics, telescopes, and equations. Before you, only a silence that has never been broken. You take a step forward, not with feet, but with thought, into the outermost question. Where does existence stop? And if it doesn't, if it simply stretches forever, what then does that even mean? The concept of the edge of the universe is both ancient and entirely modern. It haunted the imaginations of early mapmakers who inked dragons into the margins of the known world, and still haunts cosmologists armed with supercomputers. But today, the dragons have been replaced by quantum fields, dark energy, and thermodynamic paradoxes. And the boundary, it's no longer a place, but a limit of perception, a moving frontier called the observable universe. Here's the catch. It's not the cosmos that ends, but our ability to see it. The observable universe spans about 46 billion light years in every direction, not because that's how big the universe is, but because that's how far light has managed to travel since the Big Bang, stretched by the accelerating expansion of space. When you look at a galaxy 10 billion light years away, you're not just seeing distance, you're seeing time itself unspool. You're peering into the past, but this horizon is not static. With every tick of the cosmic clock, The boundary of what we can observe grows by another light day in every direction. Yet the farther we look, the deeper into time we sink. Until we approach a wall, we cannot cross the cosmic event horizon. It is not built of atoms or photons. It is woven of time and motion. Galaxies beyond this horizon are receding faster than the speed of light due to cosmic expansion. Not because they're violating relativity, but because space itself is stretching. Imagine being at sea, on a boat with no oars or engine, watching the shore slowly disappear, not because you are moving, but because the ocean is growing between you and everything else. Eventually, that shore fades from view forever. That is our future, with distant galaxies. The cosmic event horizon defines the farthest edge of our reach. Anything beyond it, stars, galaxies, even entire superclusters, can never influence us, no matter how long we wait. And in a future ruled by accelerating expansion, this horizon will shrink relative to the cosmos. One by one, galaxies will vanish from our view. In 1 trillion years, only the nearest galaxies in our gravitational group may remain visible. The universe will seem lonelier, simpler, and more static, not because it is, but because we'll have lost our window into its depth. This unfolding isolation forces a disturbing question. Will future civilizations know they're alone simply because their telescopes cannot see far enough? Would they assume that the universe is small, static, and finite, because the evidence of its vastness has fled beyond their sky? In that sense, we are living in a cosmological golden hour, perched on a rare moment when we can still see the afterglow of creation and the fingerprints of distant galaxies. But even now, there are shadows on our cosmic map, places where our theories fail to light the way. The theory of cosmic inflation offers one such illumination. In the first split second after the Big Bang, the universe expanded exponentially, faster than light, not as a violation of Einstein's rules, but because those rules apply to matter moving through space, not to space itself. This sudden, incomprehensible expansion smoothed out wrinkles in the early cosmos, stretched microscopic quantum fluctuations into the seeds of galaxies, and gave the cosmos its apparent flatness. Flatness is a strange property. In a curved universe, light would travel in arcs, and triangles wouldn't add up to 180 degrees. But our universe, on the largest scales, seems almost perfectly flat. Cosmic inflation explains why, much like zooming in on a balloon until its curvature disappears, inflation blew up the early universe so massively that any curvature was diluted to invisibility. The implication, what we call the universe, our observable slice, is likely just a bubble in an ocean of space. That ocean, known as the inflationary multiverse, may be birthing new universes constantly. In other inflating regions far beyond our horizon, each bubble could contain different physical laws, different kinds of matter, perhaps even different notions of logic or causality, and we, like fish in a cosmic aquarium, can never peer outside our bubble to see the others. This isn't just poetic speculation. The mathematics of inflation, when taken to their logical conclusion, lead directly to the idea that the universe may be far larger and more diverse than we can observe. And if inflation is eternal, as some models suggest, it may mean that the universe has no global edge at all, just an infinite foam of pocket worlds endlessly inflating. In such a framework, the very notion of a universe is outdated. We would need to redefine existence itself not as a singular event or realm, but as a multiversal process, a field of possibility, blooming without beginning or end. But there's something sobering in this grandeur. If universes are so easily spawned, then what makes ours special? Why does it contain life, consciousness, memory, and dreams? Here, the idea of fine-tuning enters. The constants of our universe: gravity, electromagnetism, the mass of particles are delicately balanced. A slight variation, and atoms wouldn't hold, stars wouldn't ignite, chemistry wouldn't unfold. If there are infinite universes, then perhaps we simply live in the one where life can exist, a cosmic lottery, where winning is rare, but inevitable, given enough tickets. And yet, even if this multiverse is real, we cannot see it. Our observable bubble remains our only lighthouse in a sea of eternal darkness. We search its edges with instruments tuned to the oldest light, the cosmic microwave background, the afterglow of the moment when the universe became transparent. This light, a relic of 380,000 years after the Big Bang, is nearly uniform, yet its faint ripples reveal the fingerprints of quantum randomness writ large by inflation. These ripples seeded galaxies and shaped the cosmic web. They are a bridge between the micro and the macro, between vacuum fluctuations and the grandeur of galactic clusters. But even here, at the limits of what we can observe, strange anomalies whisper, cold spots, asymmetries, potential signatures of a collision with another universe, bruises from a multiversal birth. Diversal. Whether these are artifacts or evidence remains unknown, but they hint that the veil of our cosmos may be thinner than we imagine.
What, then, lies beyond blue?
Not dragons or angels, but something perhaps more terrifying. The unknown that obeys different rules. A vacuum that births universes. A dimension in which time is not linear, space is not three-dimensional, and identity itself is an illusion. The edge of the universe is not a wall, but a philosophical crisis. It forces us to confront the fragility of knowledge, the arbitrariness of perspective, and the humility demanded by the cosmos. As we drift deeper into this realization, one truth becomes clear. The boundary we speak of is not out there. It is within us, in the limits of our comprehension, our language, our tools. And yet, we press forward, drawing constellations across the abyss. Imagine awakening not to a sunrise, but to a planet unfamiliar in shape and sky, yet still Earth. A world where the continents are strangers, where the wind tastes of minerals never cataloged,
and the stars above cast a different constellation across a breathable dusk. This is not science fiction. This is Earth 2 billion years ago.
The terrain was silent then, at least to human ears. The forests, deserts, and rivers we know did not yet exist. What lived and moved across the surface bore no resemblance to us. In the shallows of warm oceans, microbial mats breathed out oxygen, slowly reshaping the chemical fate of the planet. This was the time of the Great Oxygenation Event, a planetary metamorphosis that would ultimately make higher life possible.
It's here within this alien, ancient Earth that the question sharpens. Could intelligence have sparked, flared, and vanished long before we emerged?
At first glance, the answer seems absurd, but only because we look backward through the lens of our own history, as if intelligence is fated to wear a bipedal body, to build cities, to reach for the stars. But perhaps that's an illusion, born of proximity. Evolution does not plan, it meanders, leaps, stumbles. And time is vast enough to allow many different walks of fate. The Silurian hypothesis, introduced by climatologist Gavin Schmidt and astrobiologist Adam Frank, dares us to consider this. They posed not a claim, but a question. If an advanced industrial civilization had existed in the deep geological past, would we be able to detect it today? Their answer may be, but only barely. Geological time is not generous. The Earth is a master of self-forgetting. Over millions of years, tectonic plates churn the crust. Over hundreds of millions, entire mountain ranges rise and erode. Over billions, continents shift, oceans vanish, and every surface memory is sanded down to oblivion. The longer back you go, the fewer traces survive. Concrete crumbles within thousands of years. Metal corrodes. Plastics, though durable on human timescales, degrade over millennia. Even nuclear waste decays into geological neutrality in less than 1 million years. If a civilization had risen on Earth 1 billion years ago, its cities would be gone. Its machines would be atoms. Its monuments, if any were built, would have been ground into anonymous sediment. But not everything disappears. Some scars go deep. The Silurian hypothesis focuses on technosignatures, geochemical footprints left by industrial activity, a sudden spike in carbon dioxide, an anomalous mix of heavy metals, isotopic shifts in marine sediments. All these could betray the presence of large-scale technology, even if we cannot identify the tools. Take our own industrial age. In just 2 centuries, humanity has already left a planetary fingerprint. Fossil fuel combustion has shifted atmospheric carbon ratios. Plastic particles now reside in every ocean. Rare earth metals, once buried deep underground, now lie dispersed across continents. Nuclear detonations have seeded the atmosphere with radionuclides that will persist for tens of thousands of years. From a future geologist's perspective, these could be read as the signal of intelligent life, even if no fossils, no buildings, no machines remained. But here lies the challenge. How do we distinguish natural anomalies from intelligent ones? Nature is a superb engineer. Volcanic eruptions can alter climate. Meteorite impacts can disperse rare elements. Natural nuclear reactors, like those found in Oklo, Gabon, can mimic human designs through pure coincidence. This ambiguity makes deep-time archaeology a game of shadows. Every clue must be balanced against simpler explanations. And yet some anomalies continue to whisper. Consider the Paleocene-Eocene thermal maximum, a dramatic spike in global temperatures about 55 million years ago, linked to a massive release of carbon. The source remains debated. Methane clathrates volcanic activity, or something else entirely. The geological record does not speak plainly. Then there are strange isotopic excursions, abrupt shifts in marine chemistry, and inexplicable concentrations of certain metals in ancient strata. Singularly, they are oddities. Collectively, they are a pattern that dares interpretation. But perhaps the most intriguing idea isn't that we're missing evidence, but that we're missing what evidence should even look like. What if an ancient civilization didn't burn coal, didn't smelt metals, didn't build with stone? What if its technology was biological, its tools engineered from living tissue? What if it communicated not with radio waves, but with biochemical emissions or neural resonance? Would such a society leave behind any trace that modern geology or archaeology could interpret? The answer may well be no. It's a chilling realization that the vastness of geological time doesn't just erode stone, it erodes intelligibility. After 1 billion years, not only would a city vanish, but the very concept of the city might leave no footprint at all. Yet we continue searching. Why? Because the idea that we are the first and only intelligent beings to evolve on Earth carries an uncomfortable weight. It assumes rarity where time has offered abundance. It assumes a straight line where nature draws spirals. And if we are not alone in Earth's history, if there were others before us, then we must also face the second question. Why did they vanish? Perhaps they self-destructed. Perhaps they transcended matter. Or perhaps they simply passed a threshold. We have yet to approach a technological or ecological bottleneck that defines the lifespan of all complex societies. There's also the unsettling possibility that intelligence isn't favored by evolution, but rather tolerated briefly before its side effects entropy, imbalance, collapse selected out. This invites a haunting reframing. Intelligence may be an anomaly, not a pinnacle, a fleeting combustion in the slow oxygenation of a planet, a pattern that burns brightly and then vanishes, leaving only subtle discolorations in stone. And still, we hope. Because hope is itself a form of memory, a reaching back, a reaching forward in a small core drilled from ancient rock. A geologist
may one day detect a technosignature, an isotopic quirk, a mineral out of place, a chemical rhythm unlike any seen before. It won't be proof, but it will be a voice, faint and distant, speaking across time. You drift away from Earth, leaving its noise behind, as you float through a cosmic sea emptied of light. In this quiet, you begin to ask, where is everyone? Not just now, but always. The silence between the stars speaks louder than any signal. Imagine ancient civilizations light years away that might have risen and fallen long ago. Their radio beacons, once powerful, now fade into cosmic static. Perhaps they never mastered broadcasting into the void, or their light was extinguished before their reach could cross the gulfs. You wonder, did they even live long enough to build a cosmic signal? This leads to a deeper, unsettling puzzle. The Great Filter. Somewhere in the sequence from inert matter to star-faring intelligence lies a barrier. It may be ahead of us, or behind us. If behind, perhaps thousands of civilizations were extinguished before ever escaping their homeworld. If ahead, we might be flirting ever so dangerously with our own threshold. The silence of the universe could be the echo of filter past or a silent caution of filter future. Next, consider what intelligence might look like elsewhere. Not humans in alien skin, but minds that evolved under extreme conditions, on freezing rogue planets, inside crushing gas giants, or far beneath ice-bound oceans. Their intelligence might be post-biological, born not of flesh and blood, but of silicon, quantum fabric, or patterns of pure information. Such beings may communicate not through waves, but through the migration of data, hidden in gravitational ripples or the structure of dark matter. And if their form is so radically different, how could we even recognize them? Let your mind drift to stealth civilizations, beings who chose silence, who hid behind the cosmic curtain. Maybe they knew the danger of revealing themselves in a hostile universe. Perhaps they cloaked their megastructures, masked their emissions, even submerged themselves in virtual realities to avoid cosmic predators. What we call silence might be intentional discretion, a strategy for survival. Then there's the alluring but unnerving idea of the simulation hypothesis. Perhaps our universe is an artificial environment, a sandbox in which intelligences far more advanced than us conduct their experiments. If so, the absence of contact isn't cosmic loneliness, it's deliberate design. We could be the data points in a larger study, the chosen subjects of an experiment, or an art piece that stretches across dimensions we cannot perceive. It's as though you're an archaeologist of absence, trying to reconstruct civilizations from the gravestones of silence. But here's the paradox. What if intelligence inevitably vanishes? What if complexity itself triggers collapse? Every technological leap brings resource depletion, environmental risk, entropy, leading to implosion before expansion. Intelligent life might be universally self-limiting, a cosmic pattern written into the laws themselves. Or perhaps we're looking in the wrong period. What if cosmic civilizations left their mark
millions or billions of years ago, and their signatures have dissipated into background radiation, cosmic dust, or quantum noise. If they existed in the deep past of the cosmos, long before Earth formed, their legacy might be gone or nearly invisible today.
Now imagine this. You're not biased by biology. You're a quantum consciousness, evolving inside a black hole's event horizon, or a sentient interstellar cloud of plasma. Your awareness spans centuries in a single thought, yet you leave no footprints, just subtle perturbations in the curvature of space-time. Would we see you? Would we know such existence even counts as life?
And yet, the silence could also be a canvas, a space awaiting discovery. Maybe we're just the first to reach out, the first to design probes or unleash gravitational pulses with universal reach. If so, our moment is also an invitation. Should we define cosmic conversation? Should we build not just telescopes, but ethical protocols? Could the ultimate question be, who do we become if we choose to speak across the void?
You sense that even the question is a gift. To wonder is to light a spark. To ask is to step beyond Earth's cradle. And perhaps, somewhere in that silence, someone or something is also wondering.
Your awareness shifts now to the fabric of space-time, not just the contents of the cosmos, but the currents and textures that shape everything. Imagine drifting through an interstellar river, where gravity's ripples carry the story of every massive object in motion. Black holes, neutron stars, and galaxies all contribute to the tides, sending gravitational waves, faint yet far-reaching murmurs that we are only now learning to detect.
Remember LIGO's first detection in 2016? Two black holes, each tens of times the sun's mass, spiraled together and merged. The signal lasted only a fraction of a second. But that brief chirp passed through Earth, carrying encoded tales of the object's mass, spin, and final fate. It was the universe whispering, revealing something deeply fundamental, something previously undetectable by light or telescopes. In a sense, each gravitational wave we detect is like eavesdropping on a cosmic dialogue that spans billions of years. Now, picture the magnetic fields threading through galaxies immense, invisible tentacles shaping gas and dust, guiding star formation, even influencing the path of cosmic rays. These fields are relics of the early universe, evolving over eons. They speak of processes, yet wholly understood, a cosmic memory woven into the darkness itself. Your senses turn inward now, into the bizarre realm of the quantum vacuum, where even empty space teems with fluctuating energy. These ephemeral bubbles of virtual particles are fleeting but fundamental, giving rise to real consequences like the Casimir effect, where two metal plates find themselves mysteriously drawn together by vacuum fluctuations. These currents of the vacuum might hold keys to uniting gravity with the quantum world, a door into realms beyond our current cosmology.
But you don't linger there. The tide drifts you outward again, toward the edges of the cosmological canvas, where dark matter lurks, We cannot see it, but we feel its weight. Without it, galaxies like our Milky Way would tear themselves apart, stars flung into the void. Surveys of galaxy clusters show us that the majority of matter is unseen silent halos around galaxies, vast filaments in the cosmic web, structures that anchor the luminous islands of stars in space.
Even more enigmatic is dark energy, the silent accelerator that pushes galaxies apart. It permeates space itself, an invisible current stirring the cosmic sea, changing its destiny. Its nature remains obscure. Vacuum energy, a field yet unknown, a misread signal of gravity's breakdown on the grandest scales.
As you drift through these forces, gravitation, magnetism, quantum fluctuations, dark energy, you sense the unity hidden beneath. These are threads in a grand tapestry that connect the smallest subatomic world to the vast cosmic web, where monumental gravity collides with quantum whispers, where geometry and entropy meet. There lies the frontier of human understanding. And don't forget the cosmic microwave background, the oldest light. It carries within it minuscule ripples, seeds of every galaxy, cluster, and void. Its slight temperature variations map the ancient patterns laid down by inflation. Perhaps hidden in those fluctuations lie the signatures of forces we have yet to comprehend, echoes from beyond our cosmic horizon. Your drift continues to the concept of cosmic topology, the global shape of the universe. If space is curved back on itself, you could travel light years in a straight line and return to your origin, haunted by echoes of your departure. Scientists are testing this by searching for repeating patterns in the cosmic microwave background, looking for the hall of mirrors that would reveal a finite, folded cosmos.
Yet all of this, these waves, these fields, this dark scaffolding, these are stories of underlying structure. But what if structure itself is emergent? Some theoretical physicists suggest that space-time might not be fundamental at all, that it could arise from entanglement, information networks, or quantum bits. The fabric of reality could be a projection of more fundamental information patterns. If so, maybe what lies beyond the universe is not space, but the layer below networks of quantum entanglement, pre-space-time code from which our cosmos is woven.
As the journey nears its current crest, you sense a subtle tension between what we know and what we can imagine. We've stepped from black hole mergers to vacuum fluctuations, from gravitational waves to cosmic topology. These elements are our atlas of the unknown, guiding both our instruments and our imagination. You float now at the intersection of matter and mind, where galaxies' grandeur meets the enigma of consciousness. Amidst the cosmic web's network of dark matter and radiation, life finds a foothold, tiny, improbable sparks of organization in a sea of entropy. Molecules assemble into cells, cells into brains, and somewhere along that long journey, awareness awakens, light piercing the dark from within. Think of a neuron in your brain, communicating through electrical signals. These firings are echoes of cosmic processes, waveforms traveling through fields, energy transferring along gradients. Within us, space-time and quantum rules collaborate to create a coherent self. Our perception is not separated from the universe. It is woven into the same fabric. But what does it mean to carry awareness in a universe written largely in mathematics and symmetry? Human minds have begun to translate the stars into equations, expressed the cosmic origin of matter in particle colliders, and glimpsed the early universe in snapshots of the cosmic microwave background. Our consciousness has become a lens, focused backward in time, letting us touch and perhaps shape the very moment of creation. Yet awareness also brings paradox. You understand that every structure from atoms to galaxies is subject to entropy. That complexity is temporary. Civilizations rise. Quasar jets light up once dead galaxies. Black holes decay. Conscious beings like us are fragile players in cosmic time. Our ephemeral spark begs the question, is intelligence just a flash, doomed to fade like a supernova, or part of something larger, something cosmic? If life is woven from cosmic threads, perhaps consciousness itself could be universal, an emergent property of certain complex systems under the right conditions. In that case, wherever the cosmos has organized matter into self-reflective patterns, whether under earthly oceans or distant exoplanets, there might be communities akin to ours, asking versions of these same questions. Imagine a distant intelligence that observes its cosmic microwave background, hears its own gravitational waves, surveys its dark, energy-dominated future. Perhaps they have mapped their cosmic topology, theorized multiple universes, or speculated on the holographic nature of reality. Yet, they may remain cut off from others by the event horizon, each consciousness stranded in its own observable bubble. That loneliness deepens the philosophical stakes. If every observer is confined to their local horizon, if space itself, and perhaps time itself, is fundamentally emergent, then each intelligence may be writing a story that starts and ends within its own bubble of space-time. Communication across these bubbles might be forever impossible, but the impulse to reach beyond, to decode the boundary, to uncover what lies outside our horizon, is a powerful testament to intelligence itself. It drives us to build space telescopes, to detect primordial gravitational echoes, to send messages into the void in the hope someone or something will listen beyond the cosmic horizon. None of us yet know whether those signals will ever find another listener. But the act of asking, of probing, deciphering, imagining may be the most cosmically significant thing a mind can do. In gazing outward, we reflect on ourselves. In seeking the origin, we confront our mortality. In tracing the fate of stars, we trace the fleeting arc of our own existence. So, as you settle into silence, picture the universe stretching behind you, ancient and vast. Then, picture yourself an observer born of quantum dust, casting a question across the cosmos. What lies beyond? The answer may be forever beyond reach.
But the question matters. It binds us to the universe and to each other. And perhaps, in that shared wonder, lies a deeper kind of connection beyond space, beyond time, beyond all we know. Let this final note linger in your mind. Sleep gently closes around you. You have traveled across space-time's deep rifts, from inflation's birth to cyclic futures, from quantum voids to the emergence of awareness. You have touched the edge of the cosmic boundary and found not emptiness, but invitation. And in your question, the cosmos finds its echo.